A loaded freight train can take more than a mile to stop, and it can't swerve, not even slightly, no matter what shows up on the track ahead. Put two trains on a collision course on the same stretch of rail, and there's no driver skill on Earth that saves that situation once it's already close enough to see. But head-on train collisions are rare, genuinely rare, on a network moving thousands of trains a day. So how does an industry built around vehicles that can't steer and can't stop quickly keep that exact disaster from happening constantly? Start with why this problem is so much harder than it looks for cars. A car that sees danger ahead can swerve, brake hard, or both, usually inside a couple hundred feet, options a driver reaches for almost without thinking. A train has none of that. No swerving, no quick stop. Steel wheels on steel rail create almost no friction compared to rubber on asphalt, which is exactly why trains are efficient to run, hauling thousands of tons on relatively little fuel, and exactly why they're so slow to stop once that same low friction works against the crew instead of for them. Railroad engineers call this the brick wall criterion, and the name is deliberately blunt. Design the system to assume a train might round a bend and find something solid sitting on the track with zero warning, a stalled freight car, a rock slide, another train that simply shouldn't be there, because eyesight and reflexes were never going to be the thing that saved anyone in that scenario. The answer railroads landed on doesn't rely on anyone's eyesight at all. It relies on cutting the track itself into pieces. Divide a rail line into sections called blocks, each one long enough that a train entering it can always come to a complete stop before reaching the far end. Sized using the worst-case braking distance of the heaviest, fastest train expected to run that stretch of track, and enforce one simple rule without exception. Only one train gets to occupy a block at a time, no exceptions for a tight schedule, none for a driver who's confident they can make it. If a block is already occupied, every signal protecting the entrance to it shows red, and no other train is allowed to enter, no matter how urgent that other train's schedule happens to be, no matter how much freight is sitting behind it waiting to move. The entire collision problem gets reduced to a much smaller one, making absolutely sure the system always knows which blocks are occupied and which ones are empty, at every moment, without gaps, across every mile of track the railroad operates. The block system gets even trickier on a single track shared by trains running in both directions, which describes a huge share of railroad mileage outside busy main lines, especially in rural and mountainous territory where laying a second parallel track was never worth the cost. On a single line, the danger runs in a different direction entirely, head-on, not rear-end, two trains approaching each other on the exact same rail with nowhere to go. Railroads solve that with passing sidings. Short stretches of parallel track built at intervals along the route specifically, so one train can pull off and wait while the other passes safely by, sometimes for a few minutes, sometimes for the better part of an hour on a busy day when several trains are competing for the same stretch of single track. A dispatcher, or in older systems, a signalman working from a printed schedule, decides which train gets priority and which one waits in the siding, a call that can ripple delays down the entire line if it goes wrong, backing up freight and passenger trains alike for hours behind a single bad decision. Get that call wrong on an unsignaled line, and there's nothing mechanical stopping two trains from meeting each other in the middle of a blind curve, with no automatic red light or tripped circuit anywhere to save the moment a human miscounted. Here's the part that actually explains how this works without a person watching every stretch of track around the clock. In 1872, an inventor named William Robinson patented something called a track circuit, and it solved the occupancy problem with almost embarrassing simplicity. Run a small electrical current through the two rails of a block, weak enough to be harmless but strong enough to detect. A train's own steel wheels and axles complete that circuit the instant they roll onto the rails, bridging the gap between the two rails like a switch closing, and that connection automatically trips the signal at the entrance to red. Nobody has to see the train. Nobody has to report it, no radio call, no human judgment involved anywhere in that step. The train's own weight, sitting on its own wheels, throws the switch on its own signal, without a single human decision involved anywhere in the chain. An entirely mechanical form of honesty that never gets tired, distracted, or talked into cutting a corner. The moment the last car clears the block and rolls onto the next section, the circuit breaks again, and the signal can finally clear back to green, ready for the next train that comes along, with no delay beyond the physical time it takes the wheels to actually leave the rails. Before that invention, keeping trains apart worked nothing like this, and it was considerably more fragile. Early railroads ran on nothing but a printed timetable and strict operating rules. A train was authorized to be on a given stretch of track during a specific window, and every crew was trusted to trust the clock completely, down to the minute, every single trip, across a whole network of connecting schedules that all had to line up perfectly to work at all. There was no real-time confirmation that the track ahead was actually clear, only the assumption that everyone else was running exactly on schedule, an assumption that held right up until it didn't. One late train, one broken watch, one miscommunication, and the entire safety plan depended on nothing more than paper and good faith, with no automatic backstop anywhere in the chain to catch the mistake before two trains occupied the same stretch of track at the same time. That timetable and train order method stuck around on plenty of railroads well into the 20th century, right up until centralized traffic control and radio-based track warrants finally pushed it out for good by the 1980s, decades after the technology to replace it had already existed. Centralized traffic control solved a problem the track circuit couldn't solve on its own, a problem of coordination rather than detection. Automatic blocks could tell a system whether a section was occupied, but somebody still needed to actually route trains through junctions, sidings, and crossings across hundreds of miles of railroad, decisions a simple electrical circuit was never built to make. In 1927, the General Railway Signal Company installed the first version of what became known as CTC on the New York Central Railroad, letting a single dispatcher sit at one central console and remotely throw switches and clear signals across an entire stretch of territory. This instantaneous oversight eliminated the need for local tower operators or train crews to physically throw manual switches, allowing for the rapid routing of trains and drastically reducing the time required to navigate complex rail networks that used to demand a staffed post at nearly every junction along the line. That dispatcher can lock a train's direction of travel onto a track the instant a signal clears for it, a safeguard called traffic locking, which automatically blocks every opposing signal at the other end from ever clearing green while that train is still moving through, holding that lock in place for the entire length of the movement, not just the moment the signal was first given. Two trains simply can't get authorized onto the same track from opposite directions at the same time. The system won't let it happen, regardless of what any individual dispatcher might want in the moment, or how much pressure a delayed schedule puts on that decision, or how many angry phone calls are coming in from a yard waiting on a late connection. Open track between stations is only half the problem though, and it's usually the easier half to solve. Junctions, crossings, and switch turnouts create a different kind of danger entirely, one where two trains aren't sharing the same block so much as converging on the exact same point of track from different directions at once. Railroads handle that with interlockings, arrangements of signals and switches wired together so that clearing one route through a junction physically locks out every conflicting route at the same time, the mechanical equivalent of two doors that can't both be open at once no matter who's pulling the handles, one solid piece of hardware standing in for a rule that used to depend entirely on someone remembering it correctly. A signal can't show clear for one path while a switch is lined for a different, crossing one. The mechanism itself refuses to allow the contradiction, regardless of what a signalman might accidentally try to do at the panel, or how badly they might want to save a few minutes for a delayed train waiting on the other route. There's a small detail in how these signals actually behave that most riders never notice, and it's not an accident either. Modern signal lights are usually approach lit, meaning they sit dark most of the time and only light up once a train actually gets close enough to need to see them, staying dark for hours at a quiet junction with nothing scheduled to pass through. It saves bulb life across a signal system with thousands of lights running non-stop across an entire national network. And it also means a signal that's lit up at all is already telling a crew something worth paying attention to, instead of blending into a row of lights that are always on, regardless of whether anything's actually happening nearby. None of this replaced the need for a human crew to actually obey what the signals were telling them, and that gap is exactly what Positive Train Control was built to close. PTC layers, GPS positioning, and digital track data on top of the existing block and signal system, cross-checking a train's actual location and speed against what it's actually authorized to do at that exact moment, and if a train is about to run a red signal, exceed a safe speed for the track it's on, or enter territory it was never authorized to enter. The system can apply the brakes itself, without waiting for the crew to react first. It's not a replacement for block signaling. It's a second, independent check riding on top of the same century-and-a-half-old idea. They're specifically for the moment a human misses something the signal was already trying to say. A fatigued crew member, a distracted glance, a moment of bad judgment on an otherwise routine trip. The exact kind of ordinary human lapse. A purely mechanical block system was never designed to catch on its own, built for the rare day when everything else in the chain worked exactly as intended and a person still missed it. So the actual answer to how trains cross each other without colliding traces back to a genuinely simple trick from 1872, older than the automobile, older than powered flight, older than almost every other piece of transportation technology anyone takes for granted today. Let a train's own weight complete an electrical circuit, and let that circuit make the safety decision automatically, faster and more reliably than any person watching the horizon ever could. Everything built since then, the centralized dispatchers, the traffic locking, the interlockings, the GPS overlays, sits on top of that same basic idea instead of replacing it. 150 years of engineering that never actually needed to reinvent the core trick, only reinforce it, layer after layer, each one catching a failure mode the last one couldn't. So here's the question worth sitting with. If the safest part of the entire system is the one piece that never has to think, make a judgment call, or have a good day, the part that's just steel touching steel and a circuit closing, what does that say about how much we should actually be trusting human attention with the parts of the system that still depend on it, the parts nobody's figured out how to automate away yet?